All right, so let's go ahead and pick up where we left off last time. So a good spot for us to pick up is recalling what was our formula or definition for the slope of the tangent line. Does anyone remember what that one was? The one that involved the limit and had an h in there somewhere. Does anyone remember that whole definition?
Is it M tan equals um f of a
F of a.
minus f of a plus h
You're along the right track. We'll actually start off with a plus
oh,
h
yeah,
minus f of a.
of a.
And then we actually took the limit as h goes to 0. This is sort of how we got the slope of the tangent line, or there are other fancy names that we had for it, stuff like the instantaneous slope or the instantaneous rate of change, stuff like that. So what this does is that it gives us the instantaneous slope at some point a comma f of a. So like you would have some point a comma f of a, that would be your fixed point. And then we would figure out what happens to the limit as h goes to 0. So this was more or less our big topic for last time. And we did an example with it um, that we had here. Let me try to this is over here. We had that definition of the limit, definition of the instantaneous slope. And we did our example like so with 9 plus 2x squared. And basically everything we did can be pretty much summed up to what I have here. This chart sums up all of those definitions that we've talked about, either in this class or you might have talked about it in an algebra class more or less. So for a linear function, when you had a line, for example, and you want its slope, then you use the points x1, y1, x2, y2, and the slope was always y2 minus y1 over x2 minus x1, rise over run. That's what you did in algebra. Whenever we start talking into calculus, we start talking about this definition, where the average rate of change was f of x minus f of a over x minus a, which was still y2 minus a y value over x2 minus some other x value. And then we translated it to an instantaneous rate of change by taking the limit. In this case, as x goes to a. And then by doing some more modifications to our points, instead of using x1, y1, or a comma f of a, I then translate to have some definition involving an a plus h, which again, despite all of this different terminology, this different notation, it still boils down to a y value minus a y value over, and then we said last time an x value minus an x value, because we had a plus h minus a, which is why we have h on the bottom. So again, all these things are actually still derived from that base concept of what we know about slope of a linear function. We're just putting a spin of calculus on it. So this table summarizes all of those previous slides that we have worked on before. And this is just mainly for the recording that I have. If someone here happens to be watching the recording, I didn't get a recording of the last lecture. It talked about these topics here. All right, so let's go ahead and move on from this topic. And what else can we deal with regarding these limits of the average rate of change, instantaneous rate of change, and all of that? So we are finally here at the point where we introduce the derivative at the point or x value a. The derivative of a function, which we're calling f, at a. And we're going to use the notation f, and it looks like an apostrophe, but this is pronounced f prime of a. So if you see f prime of a, that means the derivative of f at A. And we define it using either one of these two definitions. F prime of A is either the limit as x goes to A of f of x minus a, f of A over x minus A, or we can use f prime of A is equal to the limit as h goes to 0 of f of A plus h minus f of A all over h. So something about this definition should look a little bit familiar to what we just saw in the previous slide. Yeah, this is actually exactly m tangent, the slope of the tangent line. That is both of these are still m tangent. And you can write the same thing here. These are the exact same definitions from before. Another way you can define this is that the derivative at A is the instantaneous rate of change at A, because they are the same formulas. If I want to be a little bit broad in my, well, not really broad, it's actually an analogous thing. The derivative, you can think of that as saying the slope of my function at A. Because we have this equality, the derivative is equal to this limit, which is the exact definition of the slope of the tangent line. So that means anytime you think of derivative, you can think that it's just a fancier word for us saying the slope of the function. But before, the reason that we don't use the same definition technically is that we really use slope for a linear function, something that's a straight line. But we know that there's a lot of graphs where they're kind of curvy, they have all these arches or anything like that. So we use this new term called the derivative. So derivative and slope, their essence, when you boil it all down, is still the same thing. If you want to think about it, derivative is just an extension of what we know about slope. All right, so of these two definitions, the one that I primarily use and the one that I would recommend is using the second one here on the right. This is probably the more commonly used one to my knowledge, or at least what I've used. Primarily also because whenever we start doing calculations, as it turns out, this right side will turn out to be a little bit nicer. The initial setup might be a little bit more difficult, but in the long run, it turns out to be a little bit nicer for calculating everything. All right, so make sure that you copy down at least this right definition for sure. All right, so we have the derivative of a function, which if I boil it down, just means the slope of the function at some value, some x value, which we call a. And then this is just me mentioning what I already had before. Again, this is still the slope of the tangent line. Another small definition that I'll mention here is that if my derivative does in fact exist, that means I can find the limit. It's some number. Then I can say that my function f is differentiable at A. So if I can find a derivative, that means we are differentiable. In particular at the point A, or x value A. So as I mentioned, this concept of this derivative is pretty much going to be a good probably 70% of this Calculus 1 course. We're going to learn more about what derivatives are, how can we apply them, how can we calculate them and stuff like that. But right now we're primarily looking at the foundations of a derivative. All right, so we have this definition of derivative and the definition of differentiable. Let's go ahead and do an example. Example 3, using the limit definition of the derivative, give me f prime of a. That is the derivative of my function at a. If I know that my function is 3x squared plus 3x, and a is equal to -2. So I'm giving you the a value already. All right, so if I want the derivative f prime of a, I need to recall that limit definition that I just had on the screen a little bit earlier, and what I asked at the beginning of class. Again, this is f prime of a is equal to, bless you, the limit as h goes to 0 of f of a plus h minus f of a all over h. So if I want f prime of a, I have to figure out what that limit is equal to. So what we're going to be doing right now is the actual calculus portion is not going to be too heavy, but the algebra portion is going to be on the heavier side, because we're going to be doing some algebraic manipulations here and there. All right, so just for notes, if I want f prime of a, and a is -2, then what I really want is f prime of -2. Again, f prime of -2. And if I just plug in for a right now, we have the limit as h goes to 0 of f of, what is it, -2 plus h minus f of -2 all over h. So all I've done here is instead of a, I'm using -2, since we said a is -2. All right, so this algebraic expression right here can get a little bit complicated. So what I'm going to do is I'm going to focus on one portion at a time. So I'm going to do a side note here. Let's go ahead and focus on this portion here, the f of -2 plus h. We're going to work on that first. So down here, right below it, I'm going to say what's f of -2 plus h. And if I want, I guess I'll go ahead and label this a little 1 here to show that I'm doing this work on the side. All right, so first off, I need to figure out what's f of -2 plus h. Where do I even start with trying to figure out what that is? If I told you I wanted f of 4, what would you do if I wanted f of 4? You would plug 4 into this function, right? Well, if I want f of -2 plus h, I'm going to plug -2 plus h into this function. So anywhere that there's an x, I'm replacing it with a -2 plus h. So I'm doing a little bit of a replacement deal. So I have 3. Instead of x, I have -2 plus h squared plus 3 times -2 plus h. And you can see why I'm doing all of these separately, just because we're getting a lot of letters flying around right now. And now I want to go ahead and try to clean this up as much as possible. And to clean this up, the first thing I'm going to do is I'm going to deal with this square right here. if I want to deal with this -2 plus h squared, well, I'm going to have to go ahead and use my FOIL term, because this is -2 plus h times -2 plus h. So I have 3 times, again, just to show you what I'm doing here, this is -2 plus h times -2 plus h. So I'm multiplying this out. So if I go ahead and FOIL, F is for first times first. What's the first times the first here? 4. Because -2 times -2, I get 4. O for outsides, what do I get? Multiplying the outsides for here. So if I multiply the outsides here and here, we're going to get -2 times h, which is -2h. Clean that up. The next part of my acronym for FOIL, I is insides. What happens if I multiply the inside terms? Yeah, looking at these, if I multiply the inside, -2 times h, I get -2h again. And then the last thing for FOIL ends with an L. Yeah, h squared. So that's this portion right here. I can also multiply this out. What's 3 times -2? Yeah, we got -6. Again, I'm just multiplying this out. And then 3 times h. Yeah, I get 3h. So again, a lot of algebra that we're moving around. All right, so the last thing I can do to simplify this, well, 2 things I can do to simplify this. What do y'all want to do next to try to clean this up? Yeah, so there's 2 things that we can do here. First thing is that these are like terms right here. -2h, -2h. So again, just for notes, I'm going to write this out. If you want, you can do all of this in one step. -2h times not times, -2h minus 2h, we get -4h plus h squared, and we still had this part at the end. And then we can multiply the 3 out. If you wanted, you could have multiplied the 3 out and then combined it. You would have ended up with the same thing one way or another. 3 times 4, we get 12. 3 times -4h, we get -12h. 3 times h squared, we get 3h squared, -6 plus 3h. Are there any like terms that I can combine here? Yeah, so we have a 12 and a -6, and a -12h and a 3h. If I combine all of these, 12 minus 6, I get 6. Clearing those up. -12 plus 3h, I get, yeah, -9h, and then plus 3h squared. So we did all this work to figure out that that highlighted region is what I have here. Again, this is a very big algebra heavy portion. Relying a lot on, do you remember how to plug stuff in, how do you FOIL, and all of this, all that stuff like that. So the good news is that we've done probably the hardest part of this problem so far. There's still a lot to do, bless you. But let's go ahead and fill in what we know so far. So if I go back up here to the top, I still have the limit. As h goes to 0, we just said f of -2 plus h. That's what we did all the way down here. So I'm just going to fill that in. That is 6 minus 9h plus 3h squared. There's still some other stuff that we need to find out. But again, all this work to figure out that that's what that highlighted region is. So I'm going to take a pause here for y'all to copy stuff down as needed. And if we have any questions about how we got F of -2 plus h. Like I said, really testing your algebra skills. This is also a primary reason why I mentioned at the beginning of the semester, it's not usually the calculus that people struggle with in calculus class, it's the algebra work that we have to use to build it up. I'm going to go ahead and erase this little portion right here. So I still need to figure out the rest of this definition. I still need minus f of -2. So we have a minus here. I guess I can go ahead and write that. How do I get f of -2 now? Yeah, so remember f of -2, I have f of x. Whenever I say give me f of -2, that's just saying anywhere that there's an x, replace it with a -2. So once again, I'm going to go ahead and write this. Let's see. Let me highlight this in a purple. I'm focusing on this portion now. I'll put a little bit of 2 in a circle to show that we're working on that now. Part 2, f of -2. Fortunately, this is not going to be as much work as that first part. Here, we're just replacing x with a -2. All right, so now we can go ahead and clean this up as needed. Using my order of operations, I know I have to deal with the exponents first. What's -2 squared? Yeah, we get 4. 4 times 3, what do I get? So this is 12 right here. And then 3 times -2, yeah, we get -6. And then here we get 12 minus 6, which leaves us with 6 again. So this other highlighted region, that turns out to be a plane 6. So I'm going to fill it in right here. And we still have h on the bottom. All right, so again, I'll take a pause here. Any questions about how I got f of -2? Probably the more preferable option compared to what we did before. All right, so now we can go ahead and try to evaluate this limit or clean it up if possible. I'm going to erase this portion down here now. So if I look at this expression, is there anything that we're noticing can probably clean up real nice for us? Yeah, we got a +6 and a -6, which means that they'll cancel out. That's perfect. Let's go ahead and write that out for notes. Usually I would just do all this together. 6 minus 6, that's definitely 0. And I'm left with -9h plus 3h squared all over h. And I say that this is even better for us. I say that we can take it a step further and simplify. Yeah, so if I look at this, the first thing I think we can all agree on is the top, everything has an h. On the bottom, we also have h's. So if I want to write this out a little bit formally, one thing I could do is on the top, I can take an h out, giving me -9 plus 3h all over h. So I'm allowed to factor out an h because it's a common factor. And here we can clearly see h divided by h, they're going to become canceling out, becoming 1. So really, let's see if I can fit it down here. The limit as h goes to 0, h cancels with h. I get -9 plus 3h. Where do I go from there? Yeah, the reason that we didn't try to put in 0 from the beginning is that I was very quickly able to see if I try to plug in 0 in the beginning, I have 0 on the bottom. That's not going to work out. But I got rid of that problem on the bottom that made me divide by 0. And so I try to plug in 0 again. What happens whenever I plug in 0 for h? What do I end up with? Yeah, we end up with a total of -9. Again, just for the sake of writing this out, I know it's a little bit everywhere. That gives me -9 plus 3 times 0, which I think we can agree is -9. So what we just did is we found out that the derivative of this function at -2 is equal to -9. But that's all great, but what does that mean for us a little bit more informally? What does it mean when my derivative at a point is -9? So I think I heard someone mention it. What did I say about my derivative? My derivative is basically a generalization of slope. So if I want to do an interpretation of this, I can say for this function, whatever this curve looks like, it's actually a parabola. If I look at x equal to -2, and I look at the slope there, the slope is -9. Or another way is, if I look at the curve at -2, I'm expecting it to go downwards with a slope of -9. And actually, this curve is going to look something along the lines of what we have. It's going to look like a U shape. So I'm expecting this probably to be somewhere here, where my slope is super steep, something like that. So again, I really want to push this idea that in the long run, the derivative is a slope at a point. The reason that it's different from what we usually know about slope is that slope is usually for flat lines, but now we have curved functions. This helps us find the slope at the point of a curved function. All right, so any questions about anything we went through on this example 3? So like I said, a lot of algebra moving around. We have to be real careful, which is why I split it up into part 1, part 2, and then actually dealing with the limit itself. All right, so the next thing I'm going to do is a little bit of an application. And I'm going to give y'all some time to think about this. This one's going to be sort of a somewhat of a word problem. Determine the rate of change of the area of a circle with respect to radius when the radius is 6 centimeters. I'm not asking you to try to solve this, but try to think about how does that idea of a derivative, being the slope, relate to this problem. So I'll give you a minute to think. Again, I'm not asking you to solve and answer this problem. Just think about how is it related to what I know about the derivative. And actually, this is a problem that we're going to see again, probably in what, 4 weeks, whenever we start really doing the more intense word problems. So if I think about derivative, I said that that's basically slope, right? And then slope, another word for slope is, well, rate of change. So if I'm looking at this problem, really another way I can interpret it is find the derivative for the area of a circle when the radius is 6 centimeters. So in other words, as the circle grows or shrinks, I can actually figure out how fast is it growing or shrinking at any given moment. And some applications that we're going to see in the future with this is that I'm going to tell you this problem because I don't give this problem because it gets a little complicated. This might be very applicable for those that are wanting to do engineering in the future. There might be an example where I say, I have a gallon of water. I pour it into a funnel and it's water is coming out of the funnel at this given rate. How long does it take for the water to leave the funnel completely, for example? And then if I want to go to more advanced examples, things that we're not going to cover in classes, like, okay, let's talk about some fluid mechanics stuff. What if I'm pouring oil instead? How is it different from whenever I'm pouring water? The rate of change for that. So a lot of applications that we will be covering. So these types of word problems, this is just primarily a preview on what we will see. And I think maybe 3 weeks is what I'm guessing, depending on our pace. And that's actually going to be something that we call related rates. Other things that we're going to do with this derivative stuff is that we're going to talk about optimization. If I give you 200 feet of fencing, what's the biggest area that you can enclose with 200 feet of fencing? Like, what's the biggest field that you can make from that? So those are all things that actually rely on the concept of a derivative. All right, so that was all for today. Tomorrow, we're going to continue talking about this topic, but more as a derivative as a function rather than the derivative at a point. All right, so like I said, that's all for today. Let me go ahead and pause this recording.